come here, and here is where I read phosphorus. Here is my range. Can you see that? Okay, now you go to the next slide, and same thing. You go here, and you look at phosphorus. Here is a delta RP. So can you see how, if you understand the concept, the answers are very simple. Is that clear, right? So when you are in the exam or homework, don't get confused. Okay, what do I do with this energy? Actually, energy is your friend here. Once you know the energy, you have, and if you do this thing in antenna, it has already got these curves there. So all you need to say is an antenna implant your energy and the dose, and it does the whole thing. So just like you saw how easy it was in antenna, when you did that, basically all you said diffuse, time, temperature, ambient, right? Same command, just one simple command where you say implant, energy, and dose. That's it. And it has all this information for you, right? Okay. So that is the thing. And that's the nice thing about my showing you how to do the problem, because sometimes students get confused. Okay, range, struggle, how do I get that information? But if you understood the point, and it comes from LSS theory. If LSS does not apply, those curves don't apply. So if I gave you a problem where I tell you that it is not amorphized, you cannot use that table. And I'm going to give you problems like this, right? I can ask you, okay, if I implant it under condition where you don't amorphize it, you got to recognize that now you cannot go to the table. It's only valid for an amorphous silicon. Okay? Okay, next question. What should be the dose if the desired peak concentration is this? So you're making a device. So remember, the circuit guys tell you I need this. From the circuit you come back, and that tells you I need a peak concentration of this for my transistor to turn on and function. We're not going to link that because the course will be too long. But from the endpoint that you want, you get the answer. You say, okay, I need a junction depth of this, and I need a peak concentration. So when you are a process engineer, you say, oh, no big deal. I can give you the answer right now. So what should be the dose if the desired peak is 10 to the 17? So I'm talking about that I want to have this number to 10 to the 17, which is very low. See, you cannot get this number by diffusion. You remember why? Because diffusion, by the time you go to 800 degrees, right, and 900, your solubility is 10 to the 19th. So how in the world you are going to get 10 to the 17th, right? But here, you can get it simply by your dose. You just adjust your dose. So that's the question here, right? So let's see how this problem is solved. So you say, okay, since dose is this formula, so you go to your next formula, and you look at it dose, so answer is right staring at you, right? You know the NP that you want, right? And you know the delta RP. So first a problem is you went into that, and this is the RP, and this is the delta RP. So that's the answer one. Now you got the delta RP, you know what dose, what is the peak concentration. So in 1 second you got your dose. So you put these numbers here, and you get a dose of 1.1 10 to the 12th. Okay. Now, this dose is very hard to even get if you do the regular pre-taper diffusion, because those numbers are very high very quickly because your surface concentrations are so high when you do the normal tube diffusion. And this was one of the advantages we talked about, that the beauty of ion implantation is that I have a very wide range of the doses, and you can see that I can tailor my dose just by these two numbers, right? So it tells me the dose, right? Okay, so I'm fine up to so far. I've got my RP, I've got delta RP, I got my dose. Okay, the next question is, how long or what is the length of time required to implant this dose into a 200 millimeter diameter wafer? So you got a 200 millimeter diameter wafer, and you are coming with the dose, right? But the question is how long a time I need to implant, because dose you only know the number, right? But you have to know the time of implant, so that's the question. So there I need to know the beam current, right? And beam current is measured when you got these ions coming at high temperature. When they hit the silicon wafer, remember there is a current integrator there, right? So you have the knowledge of beam current coming with certain velocity, because that's how you are integrating the charge in ion implantation. So now you got, so you know you know the beam current. So beam current is 2 microamp, right? And it is a singly charged phosphorus. So sometimes you will, I'll talk about it later, you may want a doubly charged, especially in the case of boron, and we will discuss that. So don't always think that it is always a singly charged ion, because there are some doubly charged ion, and for that all I have to do is to remember to adjust the magnetic field, because what you collect out of that magnetic analyzer magnet is the charge to match ratio, right? So if your charge becomes double the charge, B++, then all I have to do is to adjust my current in my magnet, electromagnet, and then I will now only get B++ coming out rather than B+. Okay, so that the question is, let us see, the answer is very, very simple, because you go to your simple formula for the dose, right? And from there, you can just rewrite the formula. The time of implant is N times Q times A times Q. This is the dose. So I got the dose from here, right? Okay, area I got it because I've given you the size of the wafer, 200 millimeters. So it is the pi r square is the area there, and N is equal to 1 and the electronic charge, and this is the beam current. So now you look at it, this is N is 1, electronic charge is this, right? And then area is your area is pi r square, right? So this is your pi r square, and then those came from here, and the beam current is this, and the answer is 28 seconds. So in 28 seconds you can do the implantation. So this is very nice. Theoretically, this whole thing is very, very nice, because the way I put these equations for you, I hope it makes it easier for you to understand all these things. And this example is another good one that brings a lot of the concepts together, right, at this time, right? Okay, then the next question is calculate the junction depths. So remember, there are going to be 2 junction depths, right? So you go to your nice simple formula, Rp delta Rp, 2 ln of Np divided by Nb, and now you know all these numbers, right? So everything is starting with Rp delta Rp, and that gives you and base is 10 to the 16, and you get 2 numbers, right? 0.12 plus or minus this number, which is 0.216 and 0.024. So you get two of these guys there at this point, right? So now I could ask a third question, that how thick an oxide should I grow if I want to implant and I only want 1 junction, right? So you can see how would you answer that, right? So what would be my junction depth how thick an oxide I will grow if I just want half the profile? How thick an oxide I need to grow? So first I would just want to get 1 junction, right? So one answer for that is your oxide thickness should be Rp. So that will be the first answer, right? I could have continued my problem here, right? Then I say, okay, what is my junction depth going to be, right? So now how would you calculate the junction depth, right? So now you look at this picture here. Okay, so in this picture, you grew an oxide which was Rp. So now you got this thing, correct? But you know this junction depth, right? Which was the deeper one, correct? And you know your Rp,
midpoint,
correct? So what is your junction depth? basically xj2 minus rp. Can you understand that? This is kind of fun things, right? Because I grew an oxide, so I killed two birds with one stone. I created one junction, right? Correct? But then I tailored my junction depth, which was not this anymore, right? Because this is from the surface, right? So now what is it? What is it going to be? You're going to go from here to there, right? Which will be your xj2, which you calculated, right, before, and that minus rp is your new junction depth. So questions like these will be on your test. I mean, if I had time, I would have put this problem on your exam, something like this. Because, you know, if you see this, and I'm trying to make it so simple and pictorial for you, but can you see that how you play the whole game? And this is how I become a great process engineer. You say, you tell me what you want, and then I can come back and say, well, you know, this is not acceptable. I want a different junction depth, right? Okay, so you say, okay, you tell me what you want, and I'm just going to grow a oxide which is of different thickness. Okay, now there you may run into a problem that your surface concentration may not work. So this is where you start playing a little bit games, you know. But you can say, okay, this is too much for you. Okay, you tell me what you want. So I said, okay, I'm just going to grow a little thicker outside and give you shallower and shallower junction, right? Is that concept getting clear? Okay, so this is real problem. This is a real life thing I'm talking about. That, you know, but as I told you, the real life problem is how do I get the junction depth I need? Because nice thing here is I have a pretty good control of my junction depth, because I can play games with the oxide thickness, right? So I have a very good control over this. But the problem is that then the requirement for the surface concentration, when you make the source and drain, right? You need certain surface concentration. If that is not met, then I have to get a different profile. Supposing this was not enough, so what would I do? I will go with a bigger dose. I raise this peak way up there, right? Right. So then, if I want this junction depth, I can have more surface concentration. I'm getting a little bit more into engineering game right now. So because, you know, you can say, well, you gave me the 0.01 micron junction depth, but you gave me a very low surface concentration, not acceptable, right? So I said, okay, what do I do? I said, okay, one thing I can go, I can lift this peak up, right? Correct? And we know how to lift this peak up by increasing the dose. So you just implant for a little longer time, right? And now until you get both the things to what you want, right? Excellent, right? So this is the true engineering. This is the real life problem I'm talking about. And this you can do with this implantation much better than you could do by diffusion. Can you see that? Because you have multiple ways of playing this game. Or you could sometimes want the reverse, because sometimes in the channel implant, you want a very low surface concentration. So you will make this guy short. So you can do many things, but mathematically also, can you understand? Because you know, if I wanted to kind of just get a taller peak, I have no problem. My dose will be thin, but profile will remain Gaussian, right? And my peak will change a little bit. Now RP will be changing. If I did it by energy, right, my RP will change. So what's the smart thing to do? You want to keep your RP and you increase the energy. Sorry, the dose, the time of implant. So I don't change my RP here, I'm just lifting the peak, right? So it kind of makes it fun, you know, that you lift the peak, and now I can give you the same junction depth with different surface concentration. Beautiful, right? That is clear, right? You understand? The tailoring, this is what you call it. If you become a process engineer someday in places like